What if everything you know about distance and reality is a fundamental illusion? Two particles, separated by light years, can react to each other instantly, as if the space between them doesn't exist. No signal, no delay, no explanation that fits neatly inside the laws of physics as we know them. Albert Einstein saw this coming in 1935, and he hated it. He called it spooky action at a distance, because he refused to accept that the universe could behave this irrationally. He spent the rest of his life trying to prove it was wrong. Today, in 2026, the evidence says Einstein lost. And it's not just a footnote in a physics textbook. This single idea that two particles can be more connected than 2 points in space should ever allow is now at the center of quantum computers, unbreakable encryption, and some of the strangest theories about the origin of space and time itself. In the next 20 minutes, we're going to dismantle the EPR paradox piece by piece. Where it came from, why it terrified the greatest physicist of the 20th century, how it was finally proven, and why, even now, it's pushing modern physics into a crisis it still hasn't escaped. To understand why this paradox mattered so much, you have to understand what quantum mechanics was doing to physics in the early 20th century. For hundreds of years, physics ran on certainty. Newton's laws told you that if you knew the position and speed of an object, you could predict exactly where it would be in the future. Cause led to effect. The universe was a machine, and if you understood the machine, you could predict its every move. Then, in the 1920s, quantum mechanics arrived and broke that machine completely. At the smallest scales, particles stopped behaving like tiny billiard balls with fixed positions and speeds. Instead, they existed in a strange in-between state, a superposition, where properties like position, spin, or momentum weren't fixed numbers, but probabilities. An electron wasn't here or there. It was, in some sense, everywhere it could possibly be, all at once, until something measured it. Only at the moment of measurement did one specific outcome collapse into existence. This idea is what physicists now call the Copenhagen interpretation, largely developed by Niels Bohr and Werner Heisenberg. And to Einstein, it sounded less like physics and more like a bet at a casino. He famously wrote to physicist Max Born that he was convinced God does not play dice with the universe. He didn't just dislike quantum mechanics. He thought it was an incomplete description of a deeper, more orderly reality that we simply hadn't discovered yet. Einstein believed in what's now called local realism, and it's built on two separate ideas. The first is realism, the belief that particles have definite, real properties, whether or not anyone is observing them. A particle has a real position and a real spin, even if we haven't measured it yet. Just like the moon still exists even when nobody is looking at it. The second is locality, the idea that nothing in the universe can influence something else instantaneously across a distance. Any influence, any cause and effect, has to travel through space, and nothing can travel faster than the speed of light. That's not just a rule of thumb. It's baked into Einstein's own theory of special relativity. So in 1935, Einstein, working with two younger physicists, Boris Podolsky and Nathan Rosen, published a paper that has become one of the most famous thought experiments in the history of science, now known by their initials, EPR. Their goal wasn't to discover something new. It was to attack quantum mechanics by exposing what they believed was a fatal flaw. Here's the thought experiment. Imagine two particles that are created together in a way that links their properties. Then you separate them, not by a few centimeters, but by an enormous distance, in principle even light years apart. According to quantum mechanics, these two particles remain entangled. If you measure a property of one particle, the mathematics of quantum theory says the corresponding property of the other particle becomes instantly determined, no matter the distance between them. To Einstein, this was absurd on its face. If measuring one particle here on Earth could instantly determine the state of a particle light years away, it would seem to require information traveling faster than light, something his own theory of relativity forbids. He believed this spooky action at a distance was proof that quantum mechanics was missing something. He argued that the particles must actually have had definite properties all along, encoded from the moment they were created. We just didn't have the tools to see them yet. He called this missing information hidden variables. In Einstein's mind, he had just delivered a knockout blow. Quantum mechanics wasn't wrong about its predictions, but it was clearly an incomplete theory, missing some deeper layer of reality that would restore common sense to the universe. What Einstein didn't realize is that he had just handed physics one of its most important discoveries. He simply assumed the answer would go his way. Because here's the unsettling question buried inside his own thought experiment. What if there are no hidden variables? What if the entanglement really is instantaneous and real, and our basic definition of distance simply doesn't work the way we assume it does? For nearly 3 decades, this question remained just that, a philosophical argument with no way to test which side was right. Einstein went to his grave in 1955 still convinced that hidden variables existed and that the universe was, deep down, orderly and local. He never got to see how the story actually ended. Before we get to how this paradox was finally tested, let's slow down and actually understand what quantum entanglement is, because the word gets thrown around a lot and most explanations either oversimplify it or make it sound more mystical than it is. When two particles become entangled, they stop being two separate, independent objects, at least mathematically. Instead, they become part of a single shared quantum state. You can't fully describe one particle without describing the other, even after they've been physically separated. It's one system, described by one equation, split across 2 locations. A common way physicists illustrate this is with a pair of gloves. Imagine you have a left glove and a right glove, and you put each one in a separate, sealed box, without looking at which is which. You send one box to a friend on the other side of the planet. The moment you open your box and see a left glove, you instantly know your friend has the right glove, even though you never communicated with them. But here's the crucial difference between the glove analogy and real quantum entanglement. In the glove case, each glove already had a definite identity, left or right, from the moment you sealed the boxes. You just didn't know which was which until you looked. That's exactly the kind of hidden variable explanation Einstein believed in. Quantum entangled particles are stranger than that. According to quantum mechanics, and according to the experiments we'll get to in a moment, the particles genuinely do not have a definite property, like spin, in either direction, until the moment of measurement. It's not that the information was hidden and we simply didn't know it. The property itself doesn't seem to exist yet for either particle until you measure one of them. And the instant you do, both particles' properties become fixed, together, correlated, no matter how far apart they are. This is what's called non-locality, and it's a direct challenge to one of the most sacred rules in physics. Nothing travels faster than light. Special relativity, one of the most rigorously tested theories we have, says that no signal, no object, no piece of information can cross space faster than roughly 300,000 kilometers per second. But the correlation between entangled particles doesn't appear to be limited by that speed at all. It doesn't seem to be traveling through space in the conventional sense. It behaves as though, for these two particles, the space between them simply isn't a barrier. To be clear, physicists are quick to point out this doesn't let you send usable information faster than light. You can't use entanglement alone to send a message because the outcome of each individual measurement still looks random from either side. You only see the strange correlation once you compare notes, and comparing notes still requires ordinary communication, which is limited by the speed of light. But the deeper mystery remains. The connection itself, the correlation, appears to exist outside of the normal rules of space and time. For decades after the EPR paper, this stayed almost entirely theoretical, a strange implication buried in the mathematics, argued about by philosophers and physicists in seminar rooms, but never actually tested in a lab. That changed as experimental physics caught up with the theory. Today, entangled photon pairs are routinely generated in labs using a process called spontaneous parametric downconversion, where a single high-energy photon passes through a special crystal and splits into two lower-energy entangled photons. These entangled pairs have been sent through fiber optic cables under cities, across open air between mountaintop observatories, and even relayed through satellites in orbit, with China's Messias satellite famously demonstrating entanglement distribution between ground stations separated by over 1,000 kilometers. The ghostly effect that Einstein dismissed as impossible is now something researchers can generate on demand, route through hardware, and measure with extraordinary precision. What was once a thought experiment designed to disprove quantum mechanics has become one of its most reliably reproducible phenomena. So, if entanglement is real and reproducible, why did it take until the 21st century for physicists to declare Einstein's local realism officially dead? The answer is that for a long time there was a mathematically valid escape hatch, a way to explain entanglement without giving up on Einstein's worldview. Remember, Einstein didn't think entanglement itself was impossible. He thought the explanation was wrong. He believed the correlations we observe could be explained by hidden variables, some kind of secret, preset information carried by each particle from the moment they were created. Like a hidden instruction manual, neither particle needed to communicate to follow, because they'd agreed on the plan in advance. No spooky influence required, just information we simply hadn't figured out how to detect yet. For nearly 30 years, there was no way to test whether hidden variables were the correct explanation, or whether quantum mechanics' stranger version of reality was correct, because both theories predicted the same basic correlations. Then, in 1964, a physicist named John Stuart Bell found a way to break the tie. Bell developed a mathematical inequality, now known as Bell's inequality, or more broadly, Bell's theorem, that made a very specific prediction. If Einstein was right, and hidden variables really did explain everything, then the statistical correlations between measurements on entangled particles could never exceed a certain mathematical limit. But if quantum mechanics was right, those correlations could, under the right conditions, exceed that limit. This was huge because for the first time, philosophy became physics. It wasn't a matter of interpretation anymore. It was a testable, measurable prediction. Scientists could actually build an experiment, take real measurements, do the statistics, and get a clear answer. Does the universe obey Einstein's local realism, or does it violate it? Starting in the 1970s and 80s, physicists began running real Bell tests. The most famous early experiments were conducted by French physicist Alain Aspect in the early 1980s, and the results consistently violated Bell's inequality, favoring quantum mechanics over local hidden variables. But critics pointed out that these early experiments had loopholes, small technical gaps in the experimental setup that, in principle, could still allow a hidden variable explanation to sneak through. For example, the locality loophole asked whether the detectors measuring each particle were truly far enough apart and switched fast enough that no signal traveling at the speed of light could possibly connect them during the measurement. The detection loophole asked whether the experiment was only catching a biased sample of particles, missing the ones that would have disproven quantum mechanics. Over the following decades, physicists worked to close these loopholes one at a time, then all at once. By 2015, several independent research groups had run what are called loophole-free Bell tests, experiments carefully designed to eliminate every known escape route for a hidden variable explanation. The results were consistent, repeatable, and unambiguous. Bell's inequality was violated. Local realism. The philosophical foundation Einstein spent his life defending does not describe our universe. This achievement was formally recognized in 2022 when the Nobel Prize in Physics was awarded jointly to Alain Aspect, John Clauser, and Anton Zeilinger for experiments with entangled photons, establishing the violation of Bell inequalities and pioneering quantum information science. It was, in a real sense, physics officially closing the book on a debate that had started with Einstein nearly 90 years earlier, and Einstein was on the losing side. More recent tests, continuing into 2026, have pushed the loophole-free experiments even further. Greater distances, faster switching, more independent random number generators feeding the measurement choices, and the result hasn't changed. The universe does not appear to hold definite, predetermined properties at the particle level before measurement happens. And yet, and this is the part that keeps physicists up at night, knowing that entanglement happens is not the same as knowing how or why it happens. We have the mathematics. We have overwhelming experimental proof. What we still don't have is a physical mechanism, a satisfying story about the actual machinery underneath reality that produces this effect. We've proven the rule. We still don't fully understand the engine running it. This unresolved why isn't a minor footnote. It sits at the center of one of the biggest unsolved problems in all of physics. Modern physics runs on two extraordinarily successful theories that, frustratingly, refuse to fit together. The first is general relativity, Einstein's theory of gravity, which describes the universe as a smooth, continuous fabric of space-time. Massive objects like stars and planets bend this fabric, and that bending is what we experience as gravity. It's an elegant, geometric theory, and it has passed every experimental test thrown at it for over a century, from the bending of starlight around the sun to the direct detection of gravitational waves. The second is quantum mechanics, which describes the universe at the smallest scales as fundamentally probabilistic, discrete, and, as we've just spent the last section proving, non-local. It also has passed every experimental test we've thrown at it, powering everything from the transistor in your phone to the lasers in a supermarket scanner. The problem is that these two theories describe reality in fundamentally incompatible ways, and entanglement sits right at the fault line between them. General relativity assumes a smooth, well-behaved space-time where cause and effect unfold locally, point by point. Quantum entanglement shows correlations that don't seem to care about that structure at all. Physicists have spent nearly a century trying to unify these two frameworks into a single theory of everything, and entanglement is one of the biggest clues and one of the biggest obstacles in that search. This collides directly with what's known as the measurement problem, one of the oldest unresolved questions in quantum theory. Before measurement, a quantum system exists in a superposition of multiple possible states. The moment it's measured, it appears to collapse into just one. But quantum mechanics' own equations don't actually describe how that collapse happens or why measurement is special in the first place. What counts as a measurement? Does it require a conscious observer or just any interaction with a large enough system? Physicists still don't agree. Because the standard explanations feel incomplete, physicists have been pushed toward genuinely radical interpretations to try to make sense of it all. The many worlds interpretation, first proposed by Hugh Everett in the 1950s, suggests that collapse never actually happens at all. Instead, every possible outcome of every quantum measurement really occurs, just in separate, branching versions of the universe that split off from each other, each one just as real as the last. Under this view, there's a version of you in a slightly different branch of reality who is currently watching a completely different YouTube video. Other physicists have seriously explored retrocausality, the idea that the choice of measurement made now could, in some sense, influence the properties of a particle in the past. It sounds like science fiction, but it's a mathematically consistent way to try to explain entanglement's correlations without breaking locality in the usual sense. It's worth saying clearly, none of these are fringe ideas from internet forums. They're published, debated, and taken seriously by professional physicists at top research institutions, precisely because the alternative, simply admitting we don't fully understand the foundations of reality, is the far more uncomfortable option for a field built on precision and certainty. And the newest thinking pushes even further than reinterpreting quantum mechanics. Some of the most cutting-edge theoretical frameworks now suggest that space and time themselves might not be fundamental at all. Instead, they might be emergent, arising from a deeper, more basic layer of information, the way temperature emerges from the average motion of countless individual molecules, without any single molecule having a temperature of its own. If that's true, then asking how entanglement can ignore distance might be the wrong question entirely, because distance itself might just be a kind of illusion generated by something underneath it. Which brings us to one of the strangest and most exciting ideas in modern theoretical physics, the ER equals EPR conjecture. Proposed in 2013 by physicists Juan Maldacena and Leonard Susskind, this idea suggests a genuinely wild possibility that quantum entanglement, the EPR from Einstein's 1935 paper, and wormholes, the ER from a different Einstein paper describing so-called Einstein-Rosen bridges, might actually be two different descriptions of the exact same underlying phenomenon. In this view, when two particles are entangled, they may be connected by an almost inconceivably small wormhole, a literal microscopic shortcut through the geometry of spacetime, rather than a mysterious correlation acting across ordinary distance. The particles aren't ignoring the space between them. In a sense, there's a hidden geometric connection, bridging that space directly. This is still a conjecture, not a proven fact, but it's a serious and actively studied one because it offers something rare, a way to connect quantum information and the geometry of spacetime within the same mathematical framework, which is exactly the kind of unification physicists have been chasing since Einstein's era. And this isn't purely academic anymore. Quantum computing research, accelerating rapidly through 2026, is actively built on entanglement's strange logic. Quantum computers use entangled qubits to process and correlate information in ways that don't follow the ordinary one-step-at-a-time timeline that classical computers rely on. Certain problems that would take a classical computer longer than the age of the universe to solve can, in principle, be tackled by exploiting exactly the kind of correlations Einstein once dismissed as impossible. Engineers and researchers aren't waiting for theoretical physicists to fully explain why entanglement works before putting it to use. They're already building real systems on top of it. So maybe the EPR paradox was never really a paradox at all. Maybe it was Einstein, accidentally, reluctantly, while trying to disprove quantum mechanics, handing physics its first real clue toward a deeper blueprint of the universe. One where space and distance aren't the fixed fundamental stage that everything else plays out on, but something closer to an illusion generated by a stranger, more connected layer of reality underneath. Einstein spent his final years trying to prove the universe couldn't be this strange. He wanted a universe that was orderly, local, and predictable. A universe that made sense the way a well-built machine makes sense. Instead, he helped discover that reality doesn't work that way at all, and we're only now, nearly a century later, starting to understand what that actually means for the nature of space, time, and everything connecting them. If this kind of mind-bending physics fascinates you, make sure you're subscribed because we're going even deeper into the ideas that are quietly rewriting our understanding of reality, one paradox at a time.